All right, the next topic, it should be the following goal. That is, suppose you have an n by n matrix. Okay. The question is A invertible? If so, what is, so to compute A inverse. Okay. All right, and our approach to this will be computational. What we've already seen in previous lecture, to find what we've seen is that in order to find A inverse, we need to solve n systems at the same time. Ax equals to E1, Ax equals to E2, all the way to Ax equals to En. Okay, we need to solve all these systems together. And now let's think about this. As we've known already, we can certainly solve each of them using row operations, as we've seen before. Now, one key point to note is that these systems, since these systems all have the same coefficient matrix, that is A, we can solve them together in the following fashion, as follows. Okay, so first of all, you form the, well, still call it augmented matrix maybe. In the sense is that you form the augmented matrix for all the systems together. Where on one side you have A, on the other side you have the columns E1s, E2s through En. And this is a matrix of size n by 2n, where the left n by n matrix is A, and the right n by n is the identity matrix of size n by n. Okay. Then perform row operations to transform A In into reduced row echelon form. Now, there's something to think about here. As we've seen already, for A to be non-singular, for A to be invertible, is the same thing as saying that A is non-singular. Again, being invertible is what we are trying to detect here. And only if A is non-singular. And being non-singular means exactly that each system, well, this is the definition of being non-singular anyway. Each system AX equals to B has unique solution. Now, we can think about this as follows. Okay. From the perspective of solving the system using row operations, what do? You form the matrix like these, right? The augmented matrix. Then you transform it into reduced echelon form. Now, for this system to have a unique solution, it's the same thing as saying that the reduced echelon form of the augmented matrix has to look like these. In on the left side, some vector d on the right side, right? Because if you think about it, what does it mean to have a unique solution? It means you can specify values of x1 is equal to something, x2 is equal to something, and so on. And that just forces you to have the left side of the reduced echelon form. Each leading one must sit in one column after the next, making the left-hand side in. Okay, so now going back to considering the invertibility of A, we can now conclude that if the reduced echelon form of A, not A, AIN, this n by 2n matrix is not of the form INB, then A is not invertible. Okay, because for A to be invertible, A must be non-singular, and A being non-singular means that AX equals to B has a unique solution. That means when you transform A, B into a reduced echelon form, it has to have I on the left side. So that means this left side here in the reduced echelon form of AIN has to be IA. Okay. So if the reduced echelon echelon long form of a I is, well, indeed of this form I n b, then what you can say is that b, then first of all, b a is invertible, and this b here that appears, this b is equal to A inverse. So now this is a complete algorithm for determining, for deciding whether A is invertible or not, and if invertible, what its inverse is, simply by forming this n by 2n matrix and perform row operations to get to reduced echelon form. Okay. So let's see how this works in practice. The amount of computation you're going to need in general is kind of huge. So we will do some sort of well-prepared, simple, small size example. Okay, so the question is invertible. And if so, what's its inverse? So what we need to do here, as I've explained, is to form this matrix. Okay, and then we have to decide, or we have to proceed to do row operations. Begin with the first row, we have to find the leading term, leading non-zero, which happens to be a 1, so that's there already. Now, we need to turn these other guys, the two entries below this leading 1, into 0. For that, we select these two operations, R2 minus 2R1 and R3 minus R1. Now this will keep row 1. R2 minus 2R1 is 2 minus 2 is 0 here. 5 minus 4 is 1. 2, that's 6. 4 minus 6 is minus 2. Now over here, we have 0 minus 2, that's negative 2. 1 minus 0 is 1. 0 minus 0 is still 0. All right. Now we have to take R3 minus R1. 1 minus 1 is 0 here. Minus 1 minus 2 is minus 3 here. 10 minus 3, that's 7 here. 0 minus 1 is negative 1 here. 0 minus 0 is 0. 1 minus 0 is 1. Okay, now we move on to the next row. Row 2, it has a leading non-zero being a 1, which we will use to get rid of the other two entries in the same column. Okay, and that requires the following operations. R1 minus 2R2 and R3 plus 3R2. That will keep R2, so that's just these guys. Now R1 minus 2R2. So I have 1 minus 0, that's 1 here. 2 minus 2, that's 0 as intended. 3 minus negative 4, that's 7. 1 minus negative 4, that's a 5. Yeah, minus 2 times 2 minus 4. 1 minus negative 4 is 5. 0 minus 2, negative 2. 0 minus 0 is 0. Good. Now R3 plus 3R2. First we have 0 plus 0, that's 0. Then minus 3 plus 1. Sorry, not 1. Minus 3 plus 3, that's 0 as intended. Now 7 plus 3 times minus 2, that's negative 6. So 7 minus 6, that's a 1. Okay. Then minus 1 plus 3 times minus 2. Minus 1 plus minus 6, that's minus 7. 0 plus 3, that's 3. 1 plus 0 is 1. Okay, so now we're done with the second row. We move on to the last row, the third row, which has the leading non-zero being a 1. So we use that to get rid of the 2 non-zero entries above it. That amounts to the following operations: R1 minus 7 R3, R2 plus 2 R3. Okay, that will keep R3, so it is still 0, 0, 1 minus 7, 3, 1, like that. So now R1 minus 7 R3. 1 minus 0, that's 1. 0 minus 0 is still 0. 7 minus 7 is 0 as intended. 5 minus, okay, now this is tricky. 5 minus 7 times 7 is 49. But it's a negative. So it's 49 plus 5, 54. Minus 2 minus 7 times 3, that's 21. So it's minus 23. 0 minus 7, that's negative 7. Okay. Now for this second row, we have R2 plus 2 R3. Again, 0 plus 0 is 0. 1 plus 0 is 1. Minus 2 plus 2 is 0 as intended. Minus 2 plus negative 14 is negative 16. Now 1 plus 6, that's 7. 0 plus 2, that's 2. Okay, so now we now arrive at reduced row echelon form, as you can see. And it's in the reduced row echelon form is I3. This is the 3 by 3 size identity matrix on the left side. So therefore, this must be A inverse on the right side. Okay. Okay, not bad, yeah. So we can let's do one more example. This example is asking for something different. So we are considering a system of linear equations like these. Okay. As we've been saying, if the coefficient matrix, if the coefficient matrix here, in this case, is 1, 2, 2, 5, if it is non-singular, then we can use it to find the solution to a linear system. Right? Let's actually do that in this example. Namely, we have written here this linear system in matrix form, and then the coefficient matrix is this one, and we want to first of all compute its inverse, and then use it to solve the system. Right? So we've seen one example, and we've seen how to do this in general. Right? For that, we have to form this matrix, and the leading one on the first row is here. So the entry before it must go, suggesting that we use this operation R2 minus 2R1. So here we have 2 minus 2 equals 0, 5 minus 4 equals to 1. 0 minus 2 is negative 2. 1 minus 0 is 1. Okay, now now the first row is completed. The second row has the leading one here. So the 2 above it must go. We can do that by performing R1 minus 2R2. That will be keep R2. 0, 1, minus 2, 1. Yes. Now, and above here, you have 1 minus 0, that's 1. 2 minus 2 is 0. 1 minus twice 1 minus 2, negative 4, that's 5. Finally, 0 minus 2 is negative 2. Okay, so now the left-hand side has been reduced to I2. This means that the right-hand side must be A inverse. Or rather, say, call this A. Okay, so A inverse is 5 minus 2 minus 2, 1. And once we have this, we can proceed to solve the linear system in the manner we've discussed before. That is, the system here has its solution being x1, x2 being given by A inverse times minus the vector minus 1 minus 10, which is that. And that's just equal to minus 5 plus 20, right? Minus 5, 20. Then 2, oops. Then the 2 minus 10. So that is 15, negative 5. Oops. Yeah, no, that's negative 8. I'm sorry. And that's That's this example. Okay, now as we've seen and expect, to carry out the process of finding the inverse of A, if existed, using this row operations in general, requires some amount of calculation, right? You have to turn things into reduced echelon form, and that takes a while. And because the right hand side of the matrix is a square matrix as well, instead of just a column, you have a lot more computations to do. Now let's consider the most basic situation, that is a matrix of size 2 by 2, and run the algorithm and see what we get. Okay, we're trying to decide, again, the purpose of the algorithm is to decide whether the matrix A is invertible or not, and if it is, what is its inverse. So to run the algorithm for this 2 by 2 matrix with entries A, B, C, D, we form this 2 by 4 matrix. Then now let's proceed. For the moment, let's pretend, let's pretend the following, right? This, we need to look at the first row, and okay, this A here may be 0 or may not be 0, right? Let's pretend it is not 0, and then we can make it 1, and then use it to get rid of the second entry C here. So suppose A isn't 0, then the following operations can be carried out. 1 over A R1, then R2 minus C R1. Okay, so 1 over A R1 will give you 1 B on A. Yes, B on 1 on A, 0. Now R2 minus C R1 would then be, well, C minus C, 0 here. What is this? D minus C B on A there. Now you would be getting 0 minus 1 over A, so negative 1 over A, times C. So negative C over A, then 1 minus 0 is 1. Okay. So now the first row is completely dealt with. Now for the second row, we would like that this highlighted entry to be the leading term, right? So for that, we will need, again, an assumption. Suppose this entry D minus CB on A is not 0, then I can turn it into 1. Yeah, that's I can divide the second row by this entry, and that will give me this. Now, okay. At this point, it's probably a good idea to simplify. Okay. So first of all, this entry is also written as A divided by AD minus BC. Right? You just multiply both the top and the bottom by A. Now, this entry here, you can process in the same fashion, multiplying both the top and the bottom by A. That'll give you minus C divided by AD times B minus BC. Okay. All right, so now we have one more thing to do, and we need to turn this matrix into reduced echelon form. That requires that we get rid of the entry B over A above this 1. So that means I need to do R1 minus B on A, R2. Now keep R2, 0, 1. Minus C, AD minus BC, A, AD minus BC. R2 remains the same. R1 becomes, well, 1 minus 0 is still 1. B over A minus B over A is 0 as intended. Now, down here, it's 1 minus 1 over A minus B over A times minus C on AD minus BC. And down here, you have negative B over A times this other guy, 1 over, maybe not this way, A, AD minus BC. Okay. Now, we need, obviously, to simplify these expressions. Over here, you see that A is just canceled with this A. So you have minus B divided by AD minus BC. Now, over here, you have something slightly more complicated. You have 1 over A minus A times AD minus BC. Another minus, it's a plus now, BC. So this is this is A times AD minus BC with in the numerator, so in the denominator, in the numerator you have AD minus BC plus BC, which, as you can see, BC, the two BC's cancel. Get AD divided by A, AD minus BC. which is D AD minus BC. Okay, so A inverse, after all these assumptions, as you remember, we assume that A is not 0 and D minus CB on A is not 0. After these assumptions, we can show that A is indeed invertible, and its inverse is this D AD minus BC minus B AD minus BC minus C AD minus BC A AD minus BC. And remember, we have the notion of scalar multiplication to matrices. That is, you can multiply a single scalar to all the entries of a given matrix at the same time. In this case, that single scalar is 1 over AD minus BC. So we arrive at this expression for A inverse. There's something to notice here. That this expression, this makes sense already when AD minus BC is not 0. Okay. Okay, so our conclusion is this. In fact, you can check the following. In fact, you can check A, B, C, D, D minus C minus B, A. If you form this product, it's AD minus BC here, 0 here, 0 here, AD minus BC. And likewise, this product in the reverse order is also AD minus BC here, 0 here, and 0 there, AD minus BC, which is 1 over, not 1 over, AD minus BC times I2. Okay, so what does this mean? This means for the matrix A with entries A, B, C, D, if AD minus BC is not 0, then A is invertible. A inverse is moreover given by 1 over AD minus BC. And that's D minus B minus C, A. If AD minus BC is 0, then A is not invertible. Okay, so in the 2x2 case, to decide, there's a very simple answer for whether a matrix of size 2 by 2 is invertible or not, it basically depends on a quantity, this quantity AD minus BC, and we will consider something like these later on for bigger matrices. Okay, so now next thing, the next discussion is about properties of matrix inverses. Okay. Right. Let's do the following theorem. So suppose A, B, both sides n by n, invertible matrices. Okay. Then, first of all, A inverse, which exists, is also invertible, and its inverse is A. Okay. 2, product AB is invertible, and its inverse, AB inverse, is B inverse times A inverse. 3, if K is a non-zero scalar, then Ka, the scalar product, is also invertible, and its inverse is 1 over K times A inverse. Now, A transpose, right, this is for n by n matrix, its transpose is also an n by n matrix. And this property says that A transpose is also invertible. And the inverse of A transpose is the transpose of A inverse. Okay, proof. One. So what do we want to do? Let's simply show that A satisfies the requirement for being the inverse of A inverse. That is, if you multiply from A to A inverse from either side, you should get the identity. But that's obvious because that's what the requirement for A inverse. So that's easy. Now, AB inverse should satisfy this property. Right? We want this, but if we start with AB and multiply A inverse, we get A inverse A, B, which is identity B, which is B. Now if we further multiply B inverse to this, we get B inverse B, which is identity. So B inverse A inverse AB, this way is the identity, but you can also group this in the same way by grouping the first two terms together. Okay, so this is telling you, at least for one of the requirements, that B inverse A inverse is a B inverse. Now the other requirement is similar. So you have AB. Let's say you multiply by B inverse. This is A, B, B inverse. So it's AI. That's A. Now AB, B inverse, A inverse is therefore A inverse, which is I. So AB, B inverse, A inverse is I. But again, you can group this product in a different fashion, like that. So this is telling you that B inverse A inverse is also a B inverse for the other requirement. That's therefore proving that the inverse of AB is B inverse A inverse. Now 3. What is 3? Okay. So you want to think about KA inverse. So let's just check that the proposed element 1 over K times A inverse is indeed good for the job. For that, we have to multiply it to KA from both sides. So first of all, you could move the scalars outside like that, and that just gives you identity. For multiplication in the other order, you just do the same trick, and again just use the statement that A inverse is A inverse. Okay, so finally, for the transpose, okay, we start with the requirement for being A inverse. And what we do now is we take the transpose of this equation. The identity transposes to itself. Now the other two things, well, you're transposing a product of two matrices, and we have seen a rule for doing that. Okay. Now you have A transpose here, you have A transpose there. Now these equalities here just tells you that whatever accompanying, whatever appears here And here is the inverse of A transpose. This must be the inverse of A transpose by the required property of inverses. And that's what we need to prove. Okay, very well. That's simple. So finally, let's summarize a few things. We've been looking at square matrices, say n by n matrix, matrix A. We've had several different notions, say non-singularity, invertibility, and so on. And the summary here is just going to tell you that there are various different looking notions that are for A that are all equivalent. Then the following equivalent one, A is non-singular. Two, columns of A, column vectors say, column vectors of A are linearly independent. Three, AX, the system AX equals B has a unique solution for any B. 4, A is invertible. 5, A is equivalent to IN. I should say row equivalent. This notion here means that A is transformed. A can be transformed to the identity matrix by row operations. Okay. Let's see. We've certainly seen one is the same as 4. That was a theorem that we proved. And let's see what else. Being non-singular means that the homogeneous system has a unique solution. The trivial solution, that follows, then it follows from the definition of linear independence that the 1 and 2 are the same. Now 2 and 3, how do we do that? Well, 3 and 4 are the same just because we can, once A is invertible, we can solve them. We can solve the system by using A inverse to get a unique answer. Then finally, we've just argued earlier that 1 and 5 are the same because if you try to, for a non-singular matrix, if you try to solve the system corresponding to it using row operations, you're going to turn that part containing A into I. Okay, so that shows that they're all equivalent. And this is the conclusion of this particular part of discussion. The next lecture, we're going to move on to vector spaces. Okay.